started. Welcome everybody to the Survival and Reproductive Success session. We're going to kick things off with Abby Dara, who is a biologist for Audubon, Mississippi. So Abby, you are welcome to take it away.
Yes, thank you. Yes, my name is Abby Dara. I'm the biologist for the Audubon, Mississippi Coastal Bird Stewardship Program. And so today I'm going to talk a little bit about some of the patterns we've seen with productivity and renesting following June tropical cyclones that have hit the Mississippi coast. Oh boy. There we go. So of course, as we all know, beach nesting birds face a number of threats due to climate change. They're very vulnerable given that they lay their eggs directly in the sand, often in close proximity to the high tide line. So they're threatened by habitat loss due to sea level rise, as well as increasing erosion rates, especially in the Gulf Coast. They're also threatened by storms, especially with potential changes in frequency, intensity, and timing of tropical cyclones. So to orient you, the Atlantic hurricane season starts on the 1st of June and lasts through the 30th of November, although the most active months are kind of late August into September. So that's, most of the storms hit when the beach nesting birds are finished and often are, migrating out of the area. But storms that hit in June coincide with peak nesting. And so storm surge can result in catastrophic or a complete reproductive failure. So not only are they vulnerable to the direct loss due to the storm surge, these storms can bring short-term habitat changes that are not necessarily beneficial. So for instance, there's a lot of debris associated with these storms. So not just trash and structural debris, but also in Mississippi, depending on the track that the storms take, it can bring in a lot of marsh grass and other sort of natural organic material just because of the marshes located directly south of Mississippi coast. And along with this comes often birds and mammals that raft on it and then die. So there's a lot of carcasses that litter the beach. And so this can attract predators. All this debris is good scavenging habitat for generalist predators. But also there's the fact that other colonial birds nest in the region that also experience widespread reproductive failure. So particularly laughing gulls, but also gall-billed terns and herons. We see, at least anecdotally, a large increase in these species on the beaches following these storms because they've lost their own nests and are just further attracted by all this debris. So when these early storms hit, there's still potentially time for the birds to re-nest, but it's not a guarantee. Re-nesting probability, there's a number of factors that affect re-nesting rate, including just species-specific characters, the date that the reproductive failure occurred, what the cause was, and et cetera. And of course, even if they do re-nest, productivity is not guaranteed. Quite frequently, regardless of storms, re-nesting efforts tend to be less productive simply because they are less optimally timed. So there's a variety of different causes for this. And then we also have to consider whether, the birds have to make a decision if they do decide to re-nest, are they going to re-nest in the same area or disperse? And in this case, it may be very hard to disperse away from areas that are affected by the storm. And so, if they do not disperse far enough, they're going to be vulnerable to these storm-driven habitat changes. And of course, how this all leads to potential population level consequences is a complicated question that I'm not going to attempt to answer today, but it is a potential concern, especially if these storms were to become more frequent. So my study objectives today are to understand how these early season, these June tropical cyclones have affected lease-term productivity during those years, and also to sort of do a preliminary analysis of how they, their re-nesting propensity. So I'm going to look at kind of three different things. One is daily nest survival probability as a function of time within the season, as well as pre and post-storm, with the hypothesis that post-storm nest survival would be lower than pre-storm because of the habitat changes and other factors, although late season, even in non-storm years, could also be lower nest survival. And of course, I hypothesize that the main cause of any post-storm nest lack of nest survival would be due to increased avian predator disturbance. So I'm going to document whether avian predators disturb or are present in the colonies more frequently after storms. And then kind of a preliminary analysis of extent and locations of re-nesting effort, including sort of some early documentation from our banding studies. So our study area is the man-made mainland beaches of coastal Mississippi, mostly in Harrison County. This is a 26-mile stretch of sand beach that can host up to over 2,000 pairs of least terns. So historically, this habitat was all salt marsh that has been developed as part of constructing for Biloxi and Gulfport. There's a 4-lane highway and a seawall just behind the beach, and the beach is regularly groomed and renourished. So it's a very artificial habitat, but the least terns really like it for the nesting substrate. And when all goes well, they can actually be quite successful in this habitat because there's relatively few mammalian predators. We think because of that 4-lane highway, we don't tend to see the foxes and raccoons that really plague least terns in other areas. So the main threats are human disturbance here and avian predators. So the data that I'm going to be presenting today were collected as part of our regular monitoring efforts for the last 4 years, 2017 and on through this past summer. So during this 4-year time period, 2 years had early tropical storms that occurred in June. So in 2017, Tropical Storm Cindy made landfall in late June, and this past year, Tropical Storm Cristobal made landfall in early June. And so in both these cases, this is pretty close to peak nesting period for least terns, where there's, most birds have eggs on the ground or young chicks. And the storm surge, overwashed all the way to the Highway 90 and resulted in complete loss of all nests and all young chicks in both years, but especially in Tropical Storm Cindy, which hit a little bit later. There were some older chicks that were able to escape the storm surge by climbing up into dunes where those were present. But we're talking about handfuls in either case. And so this is effectively 100% reproductive failure in both cases. So most of the data collected for this study is data collected as part of our regular monitoring as Audubon. We do biweekly or twice weekly colony surveys of these mainland colonies to count all nests, chicks, and fledglings. At a subset of colonies, we set up 10 by 10 meter plots, nest plots, and mark all nests inside those plots in order to follow individual nests for nest survival estimation. We also conduct regular disturbance observations. Our seasonal stewards that go out and act as sentinels record all frequency and duration of all sources of disturbance at our colonies. And for the purposes of this study, I pulled out the all observations of avian predator disturbance and compare pre and post storm. And then in 2019, we started banding adults, capturing them using drop traps on nests and putting individual field readable bands on the adults. And in 2020, especially, we ramped up our resighting efforts and made an attempt to find all nests of all marked birds. Was not always possible, but we did manage to find some, track some individuals both pre and post storm. So for the analysis, a lot of this is still kind of preliminary, but for the nest survival, I used the logistic exposure and a Bayesian framework, and kind of to simplify the issues with dates, I looked at, basically divided the season into early or late. That also corresponds with kind of pre and post storm. So looking at the effects of both time within season and the effect of a storm on daily nest survival with a colony year random effect. And I did a very similar analysis, at least in structure, for avian predator disturbance rate to look at patterns of avian predator disturbance at the colonies, both as a function of time within season and in storm years. And then for renesting rate, I haven't done any formal analysis yet, but just as a sort of a preliminary, I've estimated this as sort of the total nests across colonies pre and post storm as kind of a percentage of how many renested. So for the nest survival model, you can see that both storm and date had a negative effect on nest survival. So nest survival declines with date or in late season, regardless of the year, but this is sort of additive. So the storm has an additive effect of an additional decrease in nest survival. And you can see that in the predicted nest hatch probability. Early season, we can have quite high nest survival. This declines with later nests, and even more so if this is after one of the storms. And just a quick look at how this affects total colony productivity. I haven't, again, done any formal analysis with this yet, but this is just total productivity across the mainland coast each year. And you can see that in the storm years, it's pretty dismal compared to the non-storm years. And for avian predator disturbance frequency, was a little surprised not to see a season effect, but certainly after storm, late season after storm years. So this corresponds to post-storm. Avian predator disturbance frequency increased significantly, which corresponds with kind of just our anecdotal, evidence of, being out there and seeing these predators, taking eggs and chicks at a high rate. So there was renesting after both years, after both storms, but it was variable. In 2017, if you recall, that was the later of the two storms. It hit in late June. There was only a 7% renesting rate. There were 22 colonies pre-storm. There were 6 that reformed at their same locations, and this contained most of the renesting birds, with a relatively small percent forming a new colony several kilometers away from where we think those birds originated. 2020, when the storm hit a bit earlier in the season, there was 38% renesting rate. It seemed like a good effort. So there were 22 colonies pre-storm, 12 reformed at the same locations with 75% of renesting birds. So there were a lot of birds that renested in the same areas again, but this time 25% dispersed and reformed in new colonies, including 2 locations that were brand new for our program. So there was, a bit more evidence of dispersal and trying to find new locations. So for the banded birds, there were 12 individuals for which we were able to determine pre and post-storm nesting colonies. 5 of those renested within the same colony after the storm. They just stayed and renested, usually in a slightly different part of the colony. 7 abandoned their pre-storm colonies and moved a mean of 7 kilometers, and the range was actually like 6 to 8. It was all kind of a consistent dispersal distance, surprisingly. But notably, all the ones that dispersed left colonies that did not reform. So overall, the take-home message is that certainly June tropical storms are devastating for productivity, even if there's time for them to renest. This seems to be a function of both just a general decline in productivity with late season due to a variety of factors, but potentially exacerbated by this increase in avian predator presence after the storms. And so the majority of renesting occurred at the pre-storm locations, and even those that did disperse, 7 kilometers, they're still in the affected area. So the birds that renest, or at least the ones that we were able to find, obviously if some went off to a different state, we would not have known. But those that renested at or near their same colonies remained vulnerable to these threats. Now, what this means for population level consequences, of course, is unknown and depends very much on the frequency of these storms. I mean, I I was a little surprised to see 2 of these in the last 4 years. Maybe it's an anomaly, but it's going to take a lot more research to understand how devastating or not this is. Looking at annual survival and lifetime reproductive success and, high variation year to year, it's going to be challenging. But how to manage this situation, I have avian predator management as a question mark. It's just too large of a problem, I think, with, there's thousands of laughing gulls on the coast. What can you really do about that after these storms? And we worked with a beach cleanup crew and had them clean up, regular colony sites first so that the birds could come into clean areas, but it's just too big of a problem to really tackle in that way. So I think this just speaks to the larger importance of habitat restoration and planning for coastal resiliency to create habitats that are not so prone to complete overwash as in this, and providing habitats that can withstand storms into the future is, I think, the way to go. So I'd like to wrap up real quick by thanking our funding. Mostly these are program funders and project partners that help work with us on these beaches. And of course, Audubon staff, past and present, have all assisted with field work and the variety of various seasonals and interns that have contributed. And with that, I think maybe I have time for questions.
Yeah, we've got time for a few questions. So there's a few coming into the chat. Jeff wants to know, were you able to confirm that the new post-storm colonies contained individuals from failed colonies?
Yes, yes, this past year. So this past year was the first time we were able to document, some resites. So those 5 birds that dispersed after the storm, they came from, well, all the colonies failed, I guess, but the ones that did reform in new colonies, they left colonies that did not reform at all. Like all birds had dispersed from those colonies post-storm, if that answers your question.
He had a follow-up too. What was the minimum time it took to a pair to relay?
That's a good question. And I didn't, I kind of thought about getting that done, looking at that before this talk, and just didn't get around to it. I probably, it's hard to re-find the same birds, but I could go back and look at that. But it seemed like it was about 10 days ish, just across the board between, the birds failing and the first bird starting to relay after the storm.
Dave wanted to know, can you comment on any of the attributes of the colonies that reformed versus those that did not?
That's a really good question. And of course, I think that's the sort of next direction I should go in developing this analysis. Yeah, it's hard to know why. The beaches are so uniform here. They're all, essentially the same stretch of sand beach, but what is it? Is it the, potential factors that I would like to consider are the presence of some of these, some stretches have dunes and others don't. There could be the width of the beach. It's hard to say. One that reformed is terribly flood prone, so I have no idea why those birds resettled there, but they love that spot for some reason. Short answer is I don't have an answer, but I think that's a really good thing to look at.
Great. Pat said, when you said that 7 colonies did not reform, what did you mean by that?
So those locations were completely abandoned. No, like that particular site, no birds renested in it. So the individual birds might have renested, but not at that spot, and nothing reformed in that spot.
All right, we'll do one more, I think. Did the reformed colonies have the same or very similar numbers of nests as the original colonies? So a size comparison.
Yeah, no, and it was kind of all over the place, especially between years. In 2017, all of them were much smaller simply because very few birds attempted to renest. This past year was very strange. There were 2 colonies that must have tripled in size. It's like probably the same birds stayed, and they attracted dispersers from other colonies that decided not to renest. So one went from just ballpark, I think maybe 90 pairs pre-storm and ended up like 300 or 400 post-storm. So there was a lot of variation in that.
Great. Well, thank you so much, Abby. You can stop sharing your screen, and we have Michelle coming up next. And there's a couple more questions in the chat for you.
Okay.
All right. So we've got Michelle Stanchiel. You can correct me, Michelle, presenting next. And I just want to remind everybody, we are recording the sessions, and you can add your questions to the chat kind of as we go along. So we'll get to those after the talk. All right, take it away, Michelle.
Thanks, Anna. Good morning, everyone. As Dave suggested this morning in the Slack channel, I first want to acknowledge that I'm giving this presentation today from the traditional lands of the Haudenosaunee people of the Onondaga Nation. And then I also want to acknowledge my co-author and former PhD advisor, Jonathan Cohen. And today I'm going to be sharing some of the work from my dissertation looking at piping plovers and factors limiting abundance and productivity in the state of New Jersey. So successful recovery of endangered species requires a thorough understanding of factors that limit both population size and population growth rate. And we know that high quality habitats are associated with positive population growth rates and are sources of immigrants, whereas low quality habitats are associated with negative population growth rates and are known as sinks. And we also know that animals use information from the environment to estimate habitat quality and then decide where to live and breed. So in theory, animals will settle in the high quality habitat until it totally fills up, and then the remaining individuals are forced to settle in a lower quality habitat. But it's also possible that a low quality habitat may be chosen over a high quality habitat, and this is known as an ecological trap. So ecological traps occur when there's a mismatch between the cues for an animal to select that habitat and the actual quality of the habitat. So in other words, when the habitat that the animal chooses appears to be higher quality than it actually is, we refer to this as an ecological trap. And nest site selection within an ecological trap is typically associated with higher predation rates and lower fledge success. And this has been demonstrated in a number of different species, including indigo buntings and great tits, which are known to fledge fewer chicks when they preferentially choose to nest in locations that are considered ecological traps. And so this is really important because ecological traps may complicate endangered species management. And so understanding the nature of them can help managers to determine factors that are limiting species recovery. So the Atlantic coast population of piping plovers was listed as threatened on the US endangered species list in 1986. And as you can see, the population has seen great recovery success through the protection and management of the ESA. On the other hand, in New Jersey, which is where our study is focused, the population has seen no increase in abundance since the time of listing. So what we know about piping plovers is that nest site selection is driven by the proximity to what we call moist substrate habitats. So these are things like bayside tidal flats and ephemeral pools. And this is important in the state of New Jersey, where most of the nesting and foraging habitat is separated by human development. So this is kind of the basis for how this ecological trap in New Jersey might be established. So adult piping plovers may choose to nest on the ocean side if it's located nearby that adequate foraging habitat, despite the fact that there might be physical barriers like roads and buildings, because they can fly to and from that foraging habitat. But when their chicks hatch, they don't have access to that same foraging habitat, and so they're limited to foraging in the oceanside intertidal zone and rackline. And beaches that were relatively devoid of humans at the beginning of the nesting season, they start to see really big increases in human activity just as the chicks are starting to hatch. And of course, with increases in human activity, we start to see increases in other types of disturbances, such as dogs or ORVs. So this increase in human activity leads to even more limitations in the types of foraging habitat that are available to chicks after they hatch. So if you take all of this into context, you can kind of see how the ecological trap for plovers may be established and how it may actually be impacting many stages of the piping plover life cycle. And one of the really important management tools that we use to try to mitigate the effects of this ecological trap for plovers is nest exclosures. And so this is a photo of a nest exclosure, which is just a welded wire fence that's used to protect nests from predators and increase hatch success. And so, of course, we hope that if we can hatch more chicks, then we can also fledge more chicks. And we know that exclosed nests in New Jersey are 60% more likely to survive to hatching when compared to unexclosed nests. So they work really well if the goal is to increase the probability of hatching. But it's also been demonstrated that there are some pretty big risks to adults that come with using exclosures, because predators, especially avian predators, have been known to key into these exclosures, targeting incubating adults and then leading to increases in adult mortality. So the first question for this part of our project is, how do our management actions to prevent nest predation affect piping plover population dynamics? And then how do we use our management tools, such as predator exclosures, to improve factors limiting productivity and abundance? So the objectives here were, first, to determine the relationships between adult survival, nest fate, and exclosure use. And then the second objective was to determine the relationship between nest fate and dispersal distance. So our study took place in New Jersey from 2012 to 2019, and our study sites ranged all the way from the southern part of the state in Cape May County to the northern part of the state with sites in Monmouth County. And we used daily nest monitoring data to examine the relationship between exclosure use and nest fate. So we used a multinomial logistic exposure model, and this allows us to specifically look at the probability of different nest fates. So we can look at the probability of hatching, being depredated, abandoned, or flooded at nests both with and without exclosures. And so in our model, we included a random intercept of site nested in year, and we analyzed the data in a Bayesian framework. So this model, again, specifically allows us to look at differences in abandonment rates, which is the part of the model that I'm going to talk about today. So for adult survival, we captured and color banded 509 individuals from 2012 to 2019. And then we gathered weekly resighting data, as well as data reported to us during migration and on the wintering grounds to estimate adult true survival. So we used the Barker model to estimate adult true survival. And the Barker model has 7 parameters, and these 7 parameters apply to either the primary survey occasions, which are during the breeding season when standardized surveys are done, or the interval between primary occasions, so that'd be the non-breeding season when either non-standardized surveys or opportunistic reporting occurs. And we modeled survival as well as site fidelity, but I don't have time to talk about site fidelity today, as a function of year, sex, whether the last known nest was exclosed, whether the last known nest was abandoned. And then we also included an age effect in all of the models so that we could separately model both adult and juvenile survival rates. And then we nested the exclosure and abandonment effects within the adult age category because, of course, juveniles don't nest in their hatching year, and so they cannot be exclosed or abandoned. And then we also included the number of named hurricanes in the Atlantic Ocean and the number of days below 0 at a known wintering location to examine the potential threats to survival outside of the breeding range. So then we modeled Euclidean dispersal distance as a function of sex, whether the previous nest was abandoned, and then their interaction using a linear mixed effects model with individual as a random effect in a Bayesian framework. And then we grouped dispersal into 2 categories. So we grouped them into within season dispersal and between season dispersal. So within season dispersal, examine the distance between the individual's first nest attempt and second nest attempt after a nest failure. And then between season dispersal, examine the distance between the last known nest in year T and then the first known nest attempt in the following season. Okay, so what did we find? If we look at the posterior distributions for nest abandonment, so the x-axis here represents the probability of a nest being abandoned from the time that the first egg is laid, and then the y-axis represents the density of that specific value. So in other words, the peak represents the most likely value, and then the width represents the level of certainty. So we can see from this figure that abandonment probability for nests that are exclosed is about 3.5 times higher than abandonment probability for nests that are not exclosed. So exclosed nests here in the lighter yellow. And if we look at our results for adult survival, on this figure, we have abandonment status on the x-axis and then survival probability on the y-axis. So we had strong support for the effects of sex, exclosure use, nest abandonment, and then the interaction between exclosure use and nest abandonment on adult true survival. So we found that in New Jersey, piping plovers at unexclosed nests that have not been abandoned have relatively high survival rate. So mean true survival for adult plovers in New York, which is within the same recovery unit, was 0.73. And for nests that have not been abandoned, but have been exclosed, we see a very slight decrease in survival rates. But when a nest has been abandoned, regardless of exclosure status, the annual survival probability for male piping plovers decreases dramatically. And so if you recall from the previous slide, exclosed nests are nearly 3.5 times more likely to be abandoned than unexclosed nests. And then we also see a decrease in adult survival for females, but these wide and overlapping confidence intervals suggest that there's a lot of uncertainty in the effect of nest abandonment on female survival rates. So in this figure, the x-axis represents within season dispersal distance in kilometers, and the y-axis again represents the density of that specific value. So if we look at the dispersal distance for females, which are in blue, then when a nest has been abandoned, and we saw in the previous slide, the male is likely to have suffered the consequences, we see that a nest that has been abandoned, the female is likely to disperse much farther than males or other females whose nests were lost to any other cause. So what that means is that the loss of the male at an exclosure leads to the functional loss of both adults because the female is likely to disperse away from their original territory when the male is killed. So if we then look at between season dispersal distances, we see that for males, which are in yellow, if their last nest attempt of the previous season was abandoned, then they're more likely to disperse farther from their previous season's nest location. So regardless of whether or not the male was killed, if the nest was abandoned in the previous season, the male could likely move outside of the region in the following year to find a new nesting location. Okay, so after all that, we kind of come back to this question. How do we use exclosures to improve piping plover productivity and abundance in New Jersey? Because we know they are a really important tool for increasing hatch success. But we also know that they clearly carry risks to breeding adults. So in other words, how do we balance the benefits of exclosures with the risks of using them? Because we still need to mitigate the effects of this ecological trap. And so we need to make difficult decisions regarding exclosure use. So how do we do that? Well, one really important way that we can do that is through the use of decision support tools. So decision support tools are designed to literally help decision makers make better decisions. And Abby Dara, who you just heard from, and Jonathan Cohen created Piper X, which is a decision support tool, and it can be used to help piping plover biologists decide whether or not to use exclosures at a site. So with this tool, a user can upload site-specific data, and then the tool analyzes that data to estimate the effect of exclosures on nest abandonment and predation probabilities. And then the values from that analysis are used to predict productivity for the season and adult survival, which are then combined with other demographic rates to estimate population growth rate at the site, both with and without exclosures. But most importantly, the results can support a decision to use exclosures or not, based on whether exclosures are predicted to increase or decrease population growth rate compared to not using exclosures. But I think even more importantly, what we can do with the results from our work is that we have the opportunity to use these results to refine our decision support tools, since it's becoming much clearer that demographic rates for piping plovers vary across the breeding range. And so with that, I'd like to thank the funders for this project, the National Fish and Wildlife Foundation, the U.S. Fish and Wildlife Service, and the New Jersey Division of Fish and Wildlife. And then I'd also like to thank the Waterbird Society for coordinating such a really great virtual meeting this year. And then I'd like to thank my committee members and a number of folks for helping with logistical support and just making sure that this project was moving forward. And then finally, I want to say thanks to the many people, some of them who are even on this Zoom call right now, who have submitted their resites of banded plovers both to us and to Virginia Tech, so that we might be able to use that data in our survival analysis. And if we, I think, have a few minutes, then I'd be very happy to answer any questions.
Yes, we have a few minutes for questions. You can enter them into the chat. In the meantime, I have a question. What categories are informing the Piper X model? Is it some of the same things that you presented on?
Which categories?
Like,
so
yeah.
When you enter the data into the Piper X decision support tool, you're entering nest survival. Well, you're entering your raw nesting data. So each nest check that you conduct goes into a spreadsheet, and then you enter it into Piper X, and you say whether or not in that nest check, you tell it whether or not the nest has been exclosed or not. And then it takes all of that information and then spits out some suggestions, or, well, you have to interpret them, but for whether or not you should or should not exclose at your site.
That's a great tool.
It is a great tool.
Yeah, that's, I mean, incredible. Do you know what causes the higher mortality in adults when there are enclosures, I guess, or exclosures?
Yeah, so we suspect it's avian predators. We actually have video and photographic evidence of peregrine falcons perching on top of our exclosures. We have found great horned owls inside of exclosures. We had one individual peregrine that was targeting exclosures in one season. So avian predators are the most likely, and also potentially mink.
Did you have any cases of birds moving from site A to site B in another year, then coming back to site A in the following year?
No, not to nest. We have had them come back and like prospect, but then leave and go back to, so we had a male in particular. He was, his mate was killed in an exclosure. He left the state and went to a new site, nested there, and then he came back and prospected in New Jersey, but didn't nest, and then went back to the state that it had nested in after its mate was killed.
How many regions have access to Piper X within the Piper breeding grounds? And she has a comment too. They used cages in South Dakota to relocate piping plover nests when they were going to be flooded from rising waters in the reservoir. They were useful for the plovers in identifying the new locations of nests.
So Piper X is specifically designed for Atlantic coast piping plovers. But I'm sure that if you talked with Abby and Jonathan, they might be interested in using it for Midwest plovers, but it's available to anybody who works on the Atlantic coast.
Great. And then Dave has a question. Have you modeled the trade-off between productivity and adult survival at the population level? Piper X seems like a local management tool if he's not misunderstanding.
Correct. That would be the dream, right? So now we have all of this data, and we've talked about doing things like an IPM to look at some of those trade-offs. But since I'm finished with my dissertation, that's kind of like a free time thing, and free time.
All right, we'll do one more question. Any chance of modifying exclosure design to discourage perching?
That's a great question. We've talked about it in the past, but there was also a paper that came out a long time ago where they looked at different exclosure designs, and the design that we use was the one that was recommended from that paper. So we've talked about it. We've had thoughts about how do you camouflage them, or do you put perches on, or anti-perching devices around it? I think it's a really tricky question. It's a really tricky design.
Okay, you can go ahead and stop sharing your screen. There are a couple questions left for you in the chat, or we can have more time for more questions after all the presenters. So next up, Katie, you can go ahead and share your screen.
Okay.
All right. So
Hopefully
Katie,
y'all can hear me all right?
Yep. Take it away.
Okay. Well, thanks all for tuning in. I'm happy to follow Michelle on our little plover section of the session. So to carry on and reintroduce piping plovers, they are small migratory shorebirds that were listed under the Endangered Species Act in 1986. And this followed a population decline, which was attributed in part to habitat loss, recreational use, and predation. And they occupy 3 breeding subpopulations seen here in orange. So they are listed as endangered within the Great Lakes and threatened in the Great Plains and along the Atlantic coast. And their wintering locations do vary by breeding population, but the Atlantic coast population, which is what I'll be talking about today, they winter from the Carolinas south through Georgia, Florida, and into the Bahamas and Cuba. And the annual cycle of the piping plover is typically viewed from a breeding season standpoint. So the breeding season starts in April, when most adults return to their breeding grounds and established territories. From April to June, those plovers initiate nests, and then chicks hatch just about a month later from May to July. Then most chicks fledge from July to August, and migration begins as early as July, followed by a wintering and northbound migration, which then starts that process all over again. And generally, studies have focused on things like adult survival and demographic rates during the breeding season, like nest survival and chick survival. However, these highlighted areas here, the stages from first flight through migration and wintering, are understudied. So in order to ask questions about this time period of the annual cycle, we should further divide this into stages and view it through a slightly different lens. So instead, we can view it like this. So we still have this chicks fledging down here on the bottom left from July to August, then embarking on southbound migration in July through November roughly, overwintering until about January, and then returning north from January to May, with some second-year birds that may be breeding from April to July. And population growth is ultimately influenced by breeders, and the breeding population is partially made up of second-year returning birds. So it's pretty crucial for us to investigate the factors that influence first-year survival and also migratory movement in order to fill some knowledge gaps on this first year following fledging. So we did this studying piping plovers on Fire Island and West Hampton Island. These are 2 barrier islands off the southern shore of Long Island, New York. I will be collectively referring to this area as Fire Island. And this area includes developed communities, including federal, state, and county parks, where there's pretty substantial pedestrian, beach use, and off-road vehicle use. And so managers across the system protect piping plover nesting habitat with symbolic string fencing. So that consists of signage, which you can see down here on the lower left. And that's connected by string, and pretty much just designates areas as closed to pedestrian and off-road vehicle use. So there are a number of factors that could be influencing post-fledging survival. We expected lower survival during the initial period of post-fledge independence due to predation risks while becoming accustomed to flight and without protection from parents on the natal grounds. And compared to ocean beaches, bay intertidal areas provide higher quality brood rearing habitat, and they yield higher chick survival. So natal habitat might carry over to influence fledging survival. And also body mass, which is a relatively good index of body condition, is known to influence juvenile survival in birds and in plovers, another parts of the range. So we expected that the same might be true in Atlantic coast plovers. Given that chicks hatch earlier in the season, the earlier hatched chicks typically have higher survival. We expected the same trend could be true in fledglings. And higher mortality might occur during energetically demanding migratory and wintering months. And finally, we hypothesized that there could be yearly differences in survival due to extrinsic factors like large-scale weather events. And looking at migration, we also expected that some of these factors would influence the onset of fall migration. So those being natal habitat type, body condition, fledge date, and year. So to address these questions, we surveyed our study area twice a week from April through August or September from 2013 to 2019. And all of our breeding birds have been banded since 2013. So every year following our April return, we resighted banded adults, located nests, and then monitored those nests until hatch. Immediately following hatch, we marked each chick with a uniquely identifiable alphanumeric green flag that you can see here. And then we resighted each brood every 1 to 3 days until fledge, excuse me. We recaptured chicks with butterfly nets just before they could fly, around 20 to 23 days. And we took a measurement of pre-fledging mass. And then beyond our Fire Island study area, we received resight data from auxiliary resighters, many of which were opportunistic from birders along the coast. However, resights also came from individuals and organizations conducting similar breeding season surveys to us. And then also from migratory stopover and wintering locations, some of which saw were areas where surveys were conducted through some of the years of our study. So we used a multi-state open robust design model to estimate survival, detection probability, and state transition probability of fledglings from July 1st of their hatch year to July 1st of their second year. So these models estimate other parameters. I'll only be talking about these ones today. And robust design models enable the use of primary sampling periods that are made up of multiple secondary periods. So this is the setup of this model. I'm really not going to dive too deep into methodology here, but the takeaway is that the primary period lengths changed according to the time of year. So from July 1st to August 23rd, when we were surveying our Fire Island breeding site every 1 to 3 days, our primary periods were 9 days long, and they consisted of 3 3-day secondary periods. We then shifted to 30-day primaries when we weren't conducting these regular surveys, and then moved back to 9-day primaries when we returned to regularly survey Fire Island the following year. So we defined 3 states within the annual cycle. These were post-fledging, migratory wintering, and return. So a fledgling was within the post-fledging state if they were still within the bounds of the Fire Island study area within their hatch year. They moved to the migratory wintering state once they left Fire Island. And then because some Fire Island fledglings might emigrate and then breed elsewhere, our 3rd state was a return from the non-breeding grounds. So North Carolina marks the northernmost wintering range of piping plovers. So we considered fledglings to be within the return state once they were seen north of North Carolina in their 2nd year. So this return state is really a combination of migrating birds, prospecting birds, and breeding birds. So using these 3 states, we were interested in estimating the probability of 2 transitions, those being migration probability and return probability. And we tested the influence of covariates on survival, detection, and transition parameters based on the hypotheses that I mentioned earlier. So diving into some results, we had 292 chicks that fledged from 2013 to 2018. And of those 292 individuals, we had just under 6,500 resights of those fledglings within their 1st year. And while we tested the influence of a number of factors on post-fledgling survival, none of them explain the variation within our data set. So we found that daily survival was constant across the natal grounds, migratory wintering grounds, and the return state, within an individual's first year following fledge. So first year survival was 0.36, which was within range, but on the lower end of previous estimates of post-fledgling true survival. And our study varied from these studies in that it was the first to directly assess post-fledgling survival across a 12-month period and to test for the effect of covariates. So diving into fledgling migration, here we have primary periods on the x-axis and transition probability on the y-axis. And here we're just looking at fall migration at first in yellow. So we found that fledglings were migrating from Fire Island from July 1st to September 22nd. And you'll note here this starred value at the end. This value was fixed at 1 because there were no resites of individuals after September 22nd in all years of the study. So 100% of our fledglings had to have migrated by then. So most fledglings departed Fire Island in mid-August, with the biggest migration pulse occurring from August 6th, between August 6th and August 23rd. And then the probability of migrating was higher for individuals that fledged earlier. So here we have those same primary periods on the x-axis and migration probability on the y. And then predicted migration probability for individuals that fledged on July 2nd here in yellow, July 14th in green, and July 26th in red. So as you can see, by August 23rd, 15th to 23rd, this end primary period, migration probability reached nearly 1 for individuals that fledged by July 2nd, but was still around 0.86 for those that had fledged on the 26th. And bringing this figure back in, we can now tack on second year return. So again, that's that spring migration. So second year return probability occurred across 4 primary periods, and it was fixed by May 8th. So all of our birds were north of North Carolina by May 8th. And return probability increased relatively consistently over those primary periods from February 20th to May 8th. That largest increase occurred in late April. So as we look at both of these migrations together, it's important to note that while on first glance, this figure looks as though it shows fall migration occurring over a longer period of time, both of these migrations actually occurred at comparable lengths of time, with the greatest increase in migration probabilities occurring over 18-day periods during both migrations. But ultimately, the largest transition pulse did occur in the fall compared to the spring. So fledglings persisted on Fire Island for over a month before they migrated, with later fledged birds persisting for shorter periods of time. So while we can't really pinpoint the mechanism for this, it's likely that fledglings require a relatively consistent developmental time. So departure might be delayed to allow time for knowledge acquisition about foraging, about flight, or about local surroundings. But ultimately, fledglings are driven by a circannual rhythm that helps them get out of there. So understanding plover migration timing is crucial to properly managing and protecting habitat for young birds before they migrate. So fledglings are persisting until August and September on Fire Island, but it's important to note that Fire Island beaches, that symbolic string fencing that managers put up, is often removed, and during the course of this study, it happened as early as June, July, and August through various years. So typically, managers will reopen popular beaches once they are able to confirm broods as fledged. So that's pretty important that that's the benchmark there. Given that human use corresponds to lower shorebird use and lower survival, this is pretty concerning given that fledglings are they're embarking on a lot of behaviors during this time period. So during this persistence period, fledglings are foraging, they're roosting, they may be prospecting for future nesting locations. So extending plover closure dates could protect fledglings across a number of these essential pre-migratory behaviors. And I should note too that during the course of this study from 2013 to 2019 here on this graph, the plover population experienced a 186% increase, and pair numbers from this year suggest it may be leveling off. So while we found in this study that the mortality risk to fledglings on Fire Island was really no different than in other stages across their first year, this could very well change as this population reaches carrying capacity. And fledgling production has increased year after year since 2015, and also vegetation succession continues to limit available habitat in our study area. So we expect that density dependent effects like competition and predation may very well begin to negatively influence fledgling survival. So in the future, we should continue to investigate this especially with changes in population size and habitat characteristics. And finally, just getting back to fall migration, our findings that fledglings depart from mid to late August and September is notable, given that a few other studies have looked at migration departure and stopover timing in piping plovers. So Loring and others found that piping plover adults departed their breeding grounds in Massachusetts and Rhode Island from July 19th to July 29th. And other studies have shown migratory stopover peaks in North Carolina from late July to early August and as early as July 10th in South Carolina. So that these stopover findings more closely match the findings in adult departure compared to our results in fledgling departure suggests that fledglings are either stopping elsewhere, they are less numerous, or they're simply departing later than adults. And it's likely a combination of all three of these things, but the latter is consistent with other shorebird studies that have found adults do dominate earlier migration counts and juveniles migrate later. So some of our next steps are to incorporate this. I really am looking to add adults into this analysis to inform our understanding of Fire Island plover migratory departure as it relates to age, sex, time since nesting, time since brooding, things of that nature. So stay tuned for those results. I'm excited to get that rolling. So with that, I will thank everyone that was involved in this study, the funders and collaborating agencies. This is a huge project. To our many field technicians and reciters over the years, as it may be clear, this work could not have been done without the many reciters up and down the coast, many of which are here today, so I thank you. And to the Waterbird Society for allowing me to be here and speak to you all today. And if I have some time, I can take a question or two.
And take one or two. So Jeff asked, have you looked at what percentage of the surviving piping plovers nest as second years?
Yeah, so it's usually about 6 to 25% of the birds come back and are within the breeding population in the next year. So it makes up a pretty good portion of our population.
Okay, and Jonathan said, sorry if I missed it. Was the return state based on return to the location you banded the fledglings? How was the immigration to other breeding sites accounted for?
Yeah, so the return state was simply the return into the breeding range. So we had a couple different ways we could do this. We decided to look at it mostly from a larger standpoint. So it's more than just Fire Island. Returning was really just moving back to Virginia or north in their second year. So we didn't really accommodate for where those birds were going, just that they were back in the breeding range.
All right, great. Thanks so much, Katie. There's some more questions for you in the chat, or we can hit them up after Erin's presentation.
Can everyone see my screen okay?
It looks good. You are good to go, Erin. Thank you.
Let me do this. All right. This. All right, so good morning. My name is Erin Gallagher. I am just finishing up my first year of my master's degree at the University of North Carolina, Wilmington. I'm really happy to be here today to share my research with all of you. This has been a fantastic meeting thus far. Today, I will be talking about estimating nest productivity and identifying sources of nest and chick mortality in least tern colonies in the Outer Banks. And so my study species is the least tern. As you well know, least terns are colonial water birds that nest in on the beach. Least tern colonies can be very dynamic and complex systems, varying greatly in size, shape, density, habitat type, and species composition. Least terns are a species of special concern in North Carolina, mainly due to the loss of nesting habitat, which has been most notably the result of human development and increased human recreation and commercial use of the beaches. As such, the protection of these nesting sites is of great interest to both federal and state agencies and NGOs throughout North Carolina. Here I have pictured the 4 main life stages which depict the general timeline of a colony, most importantly in a management context. So starting with an incubating bird, indicating colony initiation up through the nest phase, to hatching, at which point chicks can be separated into nestlings, which are still in the nest, and mobile chicks, which have since left the nest. The fledging of the last chick will typically signal the conclusion of a colony, again in a management context. While each of these life stages have important management implications, my research is focused around the nest and unfledged chick stages, specifically nest and chick survival. And so just a bit more context, I am the first of 3 graduate students in a 5-year cooperative agreement with the National Park Service at Cape Hatteras National Seashore. Ultimately, the overall goal of the project is to assist the National Park Service at Cape Hatteras with evaluating the efficacy of their existing protection protocols for nesting least terns. As the first graduate student, my hope is that by identifying and evaluating both human and non-human sources of nest and chick mortality, I can provide a foundation of knowledge for future stages of the project that will be focusing more on human disturbance specifically and the potential for manipulating these existing protection protocols. In order to complete this objective, I plan to measure daily survival rates for least tern nests, measure daily survival rates for unfledged least tern chicks, and identify human and non-human sources of nest and chick mortality. The management protocol for Cape Hatteras for nesting shorebirds and waterbirds, specifically colonial beach nesting waterbirds, is outlined in the Cape Hatteras Off-Road Vehicle Management Plan. The current protocol is to place symbolic signage 100 meters from a least tern nest and unfledged least tern chicks. And so this applies to pedestrians, pets, and off-road vehicles. It's a blanket protocol. So this buffer distance is based on a study from Irwin, 1989, which measured the distances at which nesting least terns exhibited a behavior called dread flight. And dread flight is basically when a portion of the colony or a majority of the colony are flushed off of their nests, typically due to a source of disturbance. Based on the distances that Irwin found in his study, he suggested 100 meters for least tern colonies, and that is what the Park Service uses today, and that is what we are evaluating the efficacy of. Most of my field sites are located on Hatteras Island due to ease of access. Since least terns typically return to sites they've nested at historically, we can anticipate about where they're going to set up. However, the exact locations are usually determined once the breeding season starts and colony initiation begins. For this project, I will be evaluating multiple colonies within Cape Hatteras National Seashore and Pea Island National Wildlife Refuge, particularly on Hatteras Island. When choosing colonies to observe, I'm looking for colonies that exhibit a diversity of colony characteristics, such as sizes, densities, habitat types, exposure to humans, and species composition, so that I can capture all potential impacts on survival, as well as to what degree those impacts affect survival. Once I choose a colony, I mark nests within that colony for observation. Nests are marked for observation during biweekly ground nest surveys, or walkthroughs, as some people call them. I'm looking for unhatched nests that have ideally just been initiated, so that nest fate can be followed throughout the entire incubation duration. Doing this will help to eliminate certain biases when I go to analyze the data later on, particularly detection bias. Once a nest is found, it is given a nest ID number and marked with a tongue depressor. Then a nest point is created in the ArcGIS online collector phone app that I use for data collection. This field map is updated in real time. So in this visual here, you can see the nest layer being populated by nest points as I move throughout this colony, collecting observations. And I utilize a zigzagging pattern of surveying in order to cover as much ground as possible between the upper and lower shell beds, trying to ensure that I'm not missing any nests. I will also input any metadata that is associated with the nest, such as colony ID, number of eggs currently in the nest, nest status, and any notes that might be useful during the field observations. This app is really the backbone of my field data collection. Since it is updated in real time, it allows me to readily share my data with my advisor, my technician, who were not in the field with me this summer, and resource managers at Cape Hatteras and Pea Island. It also allows me to notice in real time shifts in the spatial distribution of a colony, which I'll get into a bit later. These walkthroughs also present a good opportunity for me to confirm the fate of existing known nests, so hatching and failure, since I can look for direct evidence of events like predation, which you can see here, as well as hatching. So once I mark a nest, it is observed every other day to assess its status. These observations are from a distance. Vantage points are chosen to minimize the disturbance to the colony. For my data analysis, I have to know when a nest hatches, and so I choose a vantage point that gives me a good view of the eggs and nestlings within the nest cup so that I can see when these events occur. I'm also taking note of any flushing behavior caused by disturbances, and that includes the time it takes for the birds to settle down. So when a colony is disturbed, the adults flush and engage in defensive behaviors, leaving the eggs and chicks vulnerable to threats like heat and predators. Nestlings are especially at risk as they are left exposed in the nest cup, whereas mobile chicks like this chick here can find shade to get away from the heat or hide from predators. This is why making that distinction between mobile chicks and nestlings is important for the overall understanding of chick survival. I also record the number of incubating birds, mobile chicks, and nestlings, among other distinct behavior categories. This allows me to take note of the demography of these colonies, specifically the age structure. As I'm sure those of you who work with colonial species know, these colonies evolve over the nesting season. One of the biggest variations you see as the season progresses is changes in the age structure of these colonies, as well as the associated behaviors for each age stage. So at colony initiation, you have mostly incubating and loafing birds. Then as the season goes on, you start to see more chicks on the ground, and parents chick rearing along with those later nesters that are now incubating. And then eventually incubating starts winding down, and you have mostly chick rearing adults, chicks, and fledges hanging around the colony. Understanding how these changes in demography, particularly age structure, impact survival will ultimately be important to understanding some temporal variations we see within seasons for survival rates. During nest and chick observations, I'm also looking for evidence of disturbances that occur while I'm not in the field. So I'm looking for tracks that go through the colony, including pedestrian tracks. I also have access to some direct video and photographic evidence through the National Park Service and the U.S. Fish and Wildlife Service that I'm able to utilize. Recorded weather data include average daily ambient temperature, wind speed, rainfall, for the duration of each colony as well as each individual nest throughout the incubation duration. Any unusual weather events like periods of heavy rainfall and high winds are recorded because they can cause events like backshore flooding that you can see here in this picture, or tropical storms that can have multiple severe impacts on coastal ecosystems. Such events can cause acute nest loss, which may reveal certain site-specific vulnerabilities, particularly in regards to site topography and location along the seashore. Though I do have chick observations from last season, I, as of yet, do not have a way to associate a chick with a nest once it is mobile. I hope to use various chick identification techniques, such as cellular tracking technology, life tags, that would allow me to track the movement of these chicks and also evaluate survival using known fate models. Speaking of which, I will be calculating daily survival rates for least turn nests and chicks using survival analyses included in the R package RMARC. Daily survival rate is considered the probability that a nest or chick survives from one day to the next and so on. Survival models will be used to determine if daily survival rate was influenced by a variety of covariates such as nest and chick age, site variations in such as topography and location on the seashore, temporal variations within the nesting season, which may be caused by those age structures, as well as the distribution of birds and nests throughout the colony, as well as temporal variations between seasons. And then also any influence from biotic and abiotic factors, such as human presence, human activity, proximity to human development, predators, direct predation, but then also just the presence of predators in the area, weather events, habitat type, and any intra or interspecific interactions, such as those that you would see between least terns and other nesting species. So I do have some preliminary results for this project. In 2019, the National Park Service collected observations for 2 colonies on Cape Point and Cape Hatteras. There were 35 marked nests within those colonies, and of those, 74.3% hatched. And then in 2020, I collected observations for 7 colonies in Cape Hatteras and Pea Island National Wildlife Refuge. I had 291 marked nests across those 7 colonies, and 74.2% of those hatched. Preliminary estimates of daily survival rate are close to 1 for both seasons. This is to be expected considering the relatively high success rates that we're seeing in the field. I would like to point out that nest survival is only part of the overall picture of colony productivity, which is why pairing it with more comprehensive chick survival analyses will be essential to understanding overall colony productivity in the future. So that being said, in 2021, I plan to use chick identification techniques such as those I mentioned earlier to better evaluate chick survival. I also plan to refine methodologies to increase sample size and reduce sources of bias. And so I would like to point out that my season this year was delayed due to COVID travel restrictions, and so I didn't get to the field until peak nesting season in early June. And so this may have introduced some detection bias since I was not able to observe some colonies from initiation. Something else that I plan on doing in the future is spatial analyses to evaluate how disturbances like human activity influence distribution throughout the nesting season. And I want to do this because something interesting that I observed this past season is that as the season progressed and visitation rates increased, I started seeing the second and third wave of late nesters shift away from these existing boundary that they have. And this can be significant because if you think back to Irwin, the study that the protocols are based on right now, Irwin makes a point to say that their study looked at colonies that were already initiated. And so those dread flight distances that they were getting were for birds that were already incubating nests. And so there may be a difference between the response of incubating birds and prospecting birds to human disturbance. And you would see that in these later nesting phases and these birds moving away from these existing boundaries. This could be an important factor when considering temporal variations within the season, since these shifts in distribution may cause the colony to start encroaching upon other nesting species boundaries, getting too close to predator territories, just a variety of differences throughout the season. It may also indicate a certain period of time in the season that needs specific management attention. This is just a visual representation of how age structure changes throughout the season for 2 of my colonies out of the 7. One is from Cape Hatteras National Seashore down on South Beach. The other one is from Pole 47 in Pea Island National Wildlife Refuge. While these 2 colonies differ greatly in size, they follow the same basic pattern of age structure and the associated behaviors that go along with those stages. And so these changes in age structure could be significant to nest and chick survival. And an added significance of this for our project now is that the next stage of the project is going to involve more chick survival analyses and looking at chick movement and tag and banding these chicks. So it gives us a good idea going forward when we can expect to see the most chicks for tagging purposes, as well as when it would be best to go in for the lowest level of disturbance to incubating birds. I would like to thank everyone at Cape Hatteras for their support of this project over the last 2 seasons, especially for their help collecting data this past season when I had to delay my field season. I would also like to thank my advisor, Raymond Danner, Juan Zuluaga, who was my technician this summer, my lab mates, as well as everyone at Pea Island National Wildlife Refuge. And I would also like to thank all of you for watching my presentation.
Awesome. Thank you, Erin. If you have any questions, you can put them in the chat or you can unmute yourself and ask them. You have one comment in the chat already, but let's see. And then there is a question. Do you have evidence that currently nesting pairs prevent late nesting pairs from nesting in the center of the colony, forcing them to move into new neighboring areas?
I don't currently have that. However, I do plan on doing the spatial analyses, and that is one aspect that I hope to get into is densities, particularly in the center of the colony, and understanding how those densities in a colony, as well as the distances, how survival rate changes for birds on the periphery of a colony versus those in the center. And so I do hope to get a better idea of that dynamic through those future spatial analysis.
Great. And you have a couple different comments about your work going forward. I'm curious, I've never been to your site locations. Is there vehicle traffic on the beaches there?
Cape Hatteras does allow off-road vehicle use. Pea Island does not. That being said, only one of my colonies that I studied this past season was exposed to off-road vehicles. So
great. Pam was wondering if you thought a species like a crow could key in on the tongue depressors. Any thoughts on putting out some fake markers?
I haven't observed any avian depredation yet. However, and in the literature, I haven't seen anything to suggest that that could happen, but that is a good idea, and it might be helpful to do that at sites where we have cameras so that we can actually determine whether or not that's happening.
All right, and then this comment from Ian. In the first year when I tried to study nest fates of least terns, I discovered that my activities in marking nests were helping predators cue in on them. So this is what Pam was talking about. I found fox tracks following my own footprints from nest to nest. I suggest that everyone studying least terns should look out for such effects and should incorporate colonies or subcolonies monitored only remotely to detect and measure adverse effects on your own activity.
That's a great comment, and I've discussed this with a member of my committee recently, actually, the use of a control site like that. The issue that I run into with that is that my sites are heavily managed by both the National Park Service and the U.S. Fish and Wildlife Service. And so it would be hard for me logistically to find a colony that doesn't have any sort of disturbance at all. But I do understand that concern, certainly. And I think that's one of the reasons why I make a point to record any sort of tracks that I see within the colony. However, I didn't really think to associate it with my own activities in there. So thank you.
Great. And we have another 20 or